Okay, as I said, we are using this formula quite often. So given the something like if, let me explain the other way. So ln f of x, if you when differentiated, you get 1 over f of x times f prime of x. So, oh, and we have this absolute value sign here. So, so due to this, and actually since, okay, from this given integration of f prime of x over f of x dx, you get ln absolute value of f of x. Okay, so this is quite useful. Okay, and this is used several times, as you could see even today's class. Okay, so when you integrate secant x, what the trick is to multiply this function constant value 1, and instead of 1, actually you multiply secant x plus tangent x over secant x plus tangent x. And then when you multiply the secant to the functions in the numerator, you get secant x squared plus tangent x times secant x. Now, when you differentiate tangent, you get secant x. When you differentiate secant x, you get tangent x times secant x. So, so by using this formula on the left, we get the ln absolute value of the denominator, secant x plus tangent x. So that is the integral of single secant x. Okay? And of course, if you have secant x squared, then it is simply tangent x. Because when you differentiate tangent x, you get secant x squared. So, so the you can integrate in this way. For higher powers, please think about it. So if I have tangent x to the 3/3 power, then since this 3 is an odd number, what you need to do is you need to split tangent x to 3 as tangent x squared, tangent x times tangent x squared dx. And then you use this identity to replace tangent x squared with secant x squared minus 1. Okay. So when you multiply these two, you get this. So tangent x times secant x squared. So for this one, if the problem is simple, right? Because when you differentiate tangent, you get secant x squared. So, so what you can do is you can introduce u to denote tangent x. Then secant x squared times the dx will be du minus integration of tangent x. That is, as I said, sine x over cosine x. So from the first integral, you get 1/2 of u squared. And from the second integral, you get ln secant x. And since u is a dummy variable, I just introduced, okay, I need to, okay, replace this u by tangent x. And then plus constant c. Okay, so that will be the integral of tangent x to the third power. Okay, now, so far we considered some integrand where you have a product of sine and cosine or tangent and secant, and the angles are always x. I mean, the angles were the same. Sometimes we need to integrate a product of sine and cosine where the angles are different here. So, for example, sine mx second, let me. So, sine mx times cosine nx, or sine mx times sine nx, or cosine mx times cosine nx. So the angles are all different. Okay? In that case, in that case, we need to split this product, okay, using one of these identities. So cosine sine A times cosine B can be written by this, and sine A times sine B can be written by this, and cosine A times cosine B can be written by this, right? I mean, as we as we know, sine A plus B equals sine A cosine B plus cosine A times sine B, and sine A minus B is sine A cosine B minus cosine A sine B. So from this, we can derive the first. And for the second and third one, you need to remember the next cosine A plus B is cosine A cosine B minus sine A sine B, and cosine A minus B is cosine A cosine B plus sine A sine B. So if you remember this formula, we can easily derive this A, B, and C. So using this formula, we can split the product as the sum or difference of two trigonometric functions. So as an example, if I have the integral of sine 4x times cosine 5x, we can use the formula to rewrite this integrand by this one. Okay. So, and sine is an odd function. This negative x can be written sine of negative x can be written as negative sine x. So we can just integrate sine x dx plus sine 9x dx. So the integration of sine x will be negative cosine, but since I have another negative already, so the entire derivative will be just cosine x, and sine 9x is integrated to become negative 1/9 of cosine 9x. So in this way, we can calculate this integral. So as I said, if you came from engineering departments and by any chance if your work is related with some signals, then probably you will play with this Fourier series, and the integrals introduced here will be used to prove some properties of the Fourier series in many applications or in engineering departments. Anyway, this is what is done in section 2. And let's consider section 3. Oh, so before I go to the section 3, let me briefly review section 1 and section 2. Okay. So what did we consider in section 1? We considered integration by parts. Okay. So what is the integration by parts? If I have integral of f(x) g prime dx, that will be f of x gx minus integral of f prime of x gx dx. That's the integration by parts for the indefinite integral. For the definite integral, I mean, if you have some integral domain, then the formula becomes slightly changed to this, or this is f of b g of b minus f of a g of a. Okay, so this is the integration by parts. And we considered two special cases when, okay, if your integrand is some polynomial or a power in x variable times some others, then usually this polynomial or power in x will be denoted by f of x, and the remaining part will be denoted by g prime. Sometimes your integrand consists of only one function. In that case, there's a single function times 1 can be used as your integrand, and in that case, this 1 will be denoted by g prime of x, and your given integrand, the original integrand will be denoted by f of x. I will introduce some more types for the integration by parts. So usually, so this is not the okay, general rule, but usually if your integrand has some polynomial or power in x, that part will be usually denoted by f of x. And if sometimes you have a single function as your integrand, and if you need to apply the integration by parts, okay, in that case you can put this dummy 1 will be interpreted as a g prime, and f of x will be interpreted as, the single function will be interpreted as your f of x. So that is, okay, the point of section 1. And what is the point in section 2? What did we study? So here, depending on the situation, if I have sine x to the odd number, say 5 times cosine x to some number n, in that case, this 5 will be, this 5 is interpreted as 2 times 2 plus 1, meaning sine x squared. So let me choose a different number so that you can easily remember. Say if I have, say, 7th power of sine, then this 7 is interpreted by 2 times 3 plus 1. Then this 2 goes to the power of sine inside the parenthesis. Outside the parenthesis, you put 3. And one remaining sign will be located here in front of dx. And then you keep this cosine x to the n. Okay? Then this sine x squared will be replaced by 1 minus cosine x squared. And then this cosine x will be denoted by u. Then, so this will be denoted by u to the n, and cosine x squared will be replaced by u squared, and sine x dx will be denoted by du, negative du, sorry, because u is cosine x, so du will be negative sine x dx. So negative sine x dx will be replaced by negative du. Okay, so that is the way to integrate this function. So the integral of this can be performed by this. If I have sine x to the mth and say cosine x to the 7th, then we have a similar trick. This 7 is interpreted by 2 times 3 plus 1. And you keep this sine x to the m, but instead cosine x to the 7th, we split this as cosine x squared to the 3rd times cosine x dx. And then this cosine x squared will be replaced by 1 minus sine x squared. And then this sine x will be replaced by u. Then cosine x dx will be du. So here, in this case, u is representing sine x. So du will be cosine x dx. So the integration is performed like this, but and as I said, the integrand is now a polynomial in u, so you can integrate this and then you replace u with the original function, cosine or sine. And what happens if these powers of sine and cosine are all even? Say sine x squared and cosine x to the fourth dx. In that case, I need to use this formula. Cosine 2x will be 2 cosine x squared minus 1, or 1 minus 2 sine x squared. So from the upper equation, so we have cosine x squared is 1/2 of 1 plus cosine 2x. And from the bottom, we get sine x squared will be 1/2 of 1 minus cosine 2x. So using this, you replace this integrand with some expressions in cosine 2x. Okay, and then you can apply the formula like this. So please use this, okay? So this formula explains the case when the angles for sine and cosine are the same. But if the angles are different, say if I consider, say, sine 2x multiplied by cosine 3x, then you need to split. Okay? And cosine A plus B equals cosine A cosine B minus sine, oops, not this one. Since I'm considering the product of sine and cosine, sorry. In that case, I need to use the sine formula. Sine A plus B is sine A cosine B plus cosine A sine B. So sine A cosine B comes from, so the angle becomes this negative sign here. The sign becomes this. So if I add them, sine A cosine B will be the average of sine A plus B minus sine, if I add them, the average of sine A minus B will be sine A cosine B. So the integrand is 1/2 of sine A is 2x and B is 3x. So their sum is 5x plus sine A minus B is minus x dx. And at that point, so so this formula is not the only formula we need. We may need another one, another property of this sine and cosine. Sine is an odd function, meaning sine negative x will be negative sine x. So we get sine 5x minus sine x dx. So if the angles are different, then depending on this product, if you have sine times the sine or cosine times the cosine, you need to think of the expansion formula for the cosine. If you have sine times cosine but with different angles, then you need to think about the sine formula. Okay, so from this sine formula, I can easily derive this. Okay, and then using this, I can split this product as the sum of two trigonometric functions, and then you can integrate this one by one. Okay. So this is the case. And if you have the integral of tangent and secant x, then depending on the situation, okay, depending on the sometimes, for example, if you have, say, sine x, I'm sorry, not sine x, but say secant x to the fourth dx, in this situation, that was the first case, then what should I do? So in case of tangent and secant, I need secant x squared or tangent x secant x, okay, as an extra copy. So if the power of secant is even and greater than 4, greater than or equal to 4, then I can split this as secant x squared times secant x squared, so that I can put this extra secant x squared. Then the remaining secant x squared is replaced by 1 plus tangent x squared. And then you introduce u to express this tangent. In other words, the integrand is now 1 plus u squared. When I introduce u to express the tangent x, then secant x dx will be just du. So I need to integrate 1 plus u squared with respect to u variable. Then we get u plus 1/3 of u to the cube. And then you replace u in terms of x, tangent x. And then you can put the integral constant to c at the end. Okay. And if you have, for the other situation, if you have some other power over tangent and secant x, so if you have, say, other power of tangent times secant x squared dx. Okay, then you take one copy of tangent. So if the power of tangent is an odd number, then you take one copy from tangent and one copy from secant. Okay, then what are what is the remaining? We have two copies of tangent and one copy of secant. The next step is to replace this tangent x squared by 1 minus secant x squared. So that is 1 minus secant x squared times secant x multiplied by tangent x secant x dx. And then I replace u secant with u. Then the integrand is 1 minus u squared times u. And if u replaces secant x, then tangent x secant x dx will be du. If that is not clear to some students, here is the idea. If u introduces secant x, then the derivative of u with respect to x is denoted by du dx. Then what is the derivative of u? What is the derivative of secant x? That will be tangent x secant x. Once you get this, please move this dx to the other side. Okay, then du will be tangent x secant x dx. As another example, if u substitutes, say, sine x, then the derivative of u with respect to x, du dx, will be cosine x. Once you get this formal result, please put this dx to the other side. Then du can be replaced, will replace cosine x dx. So in this way, given some new variable u to represent a function in x, we can easily derive du. Anyway, in this case, we have du here. So integrand is now u minus u cubed du, and which is 1/2 of u squared minus 1/4 of u to the fourth. And as I said, this is not the final answer because currently I have some expression in u, while the original problem is asking an antiderivative of some function of x. So if I replace this u with my secant x, then that will be the correct antiderivative of the current tangent x cubed and secant x squared. Okay, so in this way, if you have a product of tangent and secant, we cannot handle every situation. But if we are lucky in the sense that the one of two conditions is satisfied, say if the power of secant is greater than or equal to 4, and if it is an odd number, then please take this, please save secant x squared. Okay? If the power of tangent is an odd number, then please save this tangent x secant x as extra copy. Okay, and then you need to split this integrand as the product of tangent x and secant x and the remaining. This remaining will define the antiderivative with new variable u. So that is what is covered in section 2. And there are many exercise problems in the textbook, so please try some examples, please. Now, so that those are what is considered in the previous section, previous class. Now, let us consider the following. If I have this integrand, x times square root of a squared minus x squared, then the problem is easy because a squared minus x squared, when differentiated, you get negative 2x. Okay? So that means if I introduce u to represent a squared minus x squared, then du dx will be negative 2x. So as I said, in that once I have this, please move this dx in the denominator to the other side. Then du will be negative 2x dx. So from this, x dx can be obtained from du by multiplying negative 1/2. Okay. Then the problem is simple because x square root of a squared minus x squared dx is square root of a squared minus x squared times x dx. And if I introduce u to substitute a squared minus x squared, then the integrand is square root of u, and x dx is negative 1/2 times du. So we get negative 1/2 times integral of u to the 1/2 du. So negative 1/2 times 2/3 times u to the 3/2, right? And then if I replace u with a squared minus x squared, we get the integral of the origin of this problem. So if I have on x this x in front of the square root of a squared minus x squared, then the integration is quite doable. I mean, we can do this calculation, right? The problem is complicated when you do not have x, but just the square root of a squared minus x squared. In that case, the substitution of a squared minus x squared by u cannot help. It cannot help because when I introduce u to substitute a squared minus x squared, I need to replace dx with du, but in order to replace the dx with the du, I need extra x. then I can replace this dx, x times dx with du. But if I do not have x, then we cannot do this. I mean, we cannot replace dx with du. So the problem in this section considers such a situation. So we want to consider the integration of the square root of a squared minus x squared without x in front. Okay? So we want to consider such problem. Now, if we change the variable x with a sine theta, so if x is replaced by a sine theta, then 1 minus sine theta squared will be cosine theta squared. So a squared minus x squared will be a squared minus a squared sine theta squared, and a squared is common, so I can rewrite this as a product of a squared times 1 minus sine theta squared, and 1 minus sine theta squared is cosine theta squared. So by eliminating this square root sign, we get a times the absolute value of cosine theta. Without the absolute value sign, the just cosine x, cosine theta can be negative. Then it is contradictory because this square root function must give non-negative value as an output. So we get this. Okay. So um, oh before so if given this square root of a squared minus x squared, if I introduce x equal, so I introduce actually new variable is a theta, and x substitutes a times sine theta, then this square root function can be written as a times the absolute value of cosine theta, right? And okay, so that is fine in the sense that I don't have the square root function, but I'm not happy with this absolute value sign. I want to eliminate this absolute value sign. Okay? So the only problem with this result of this substitution is the absolute value sign. Because I don't know how to derive an antiderivative corresponding to the absolute value of cosine theta. If I have just a single cosine theta without the absolute value sign, then its antiderivative will be sine. But since I have a absolute value, the problem will be not that simple. So we want to modify this a little bit. Okay. So please remember that given sine function, given sine function, originally the sine and cosine is a periodic function. So it is not one-to-one, so I cannot think of the inverse. But if I restrict the domain from minus half pi to half pi, then the function becomes one-to-one on that interval, so that we could think of its inverse. That's how we define the arcsine function. Right? So when I consider this arcsine function, the angle is limited to negative half pi to half pi. In a similar way, if I consider the cosine function, cosine function is not, it is also a periodic function. It is not one-to-one. So we cannot think of its inverse. However, if I restrict the angle from 0 to pi only, then the function becomes one-to-one, and we can think of its inverse function. Right? So in that case, the angle is between 0 and pi. So, given sine and sine function, if I restrict the angle to negative half pi to half pi, then sine function is one-to-one, right? So that we can think of its inverse, right? If I have, in case of tangent function, when I consider similar interval, the function becomes one-to-one, and it is invertible. And if I consider this interval for theta, the secant function will be one-to-one. Okay. So based on this, please remember this one. So first, if your integrand is the square root of a squared minus x squared type, as we did in the previous slide, then please replace x with a sine theta. Okay, but at this point, theta is limited to this interval between negative half pi to half pi. Then what happens in my previous expression? As I said, I introduced a sine theta. When I do this, I cannot think of arbitrary theta because I want to take some inverse. So theta will be limited to the interval between minus half pi and half pi. And on that interval, between minus half pi and half pi, my cosine function will be always non-negative. Okay? So moments ago, if I just consider a sine theta to replace x, at that point, from here, from the third step to the fourth, since the square root function returns non-negative value, I introduced the absolute value of cosine theta to get non-negative value. And since I want to restrict my theta to negative half pi to half pi, and on that interval my cosine is always non-negative, the absolute value sign is meaningless. So you get a cosine theta. Okay, so I can integrate this directly. So integration of this, okay, will be handled in terms of the integration of cosine theta. Okay, so I will continue on next time, but the idea is this. So I will explain in more detail next time. But since when I have this absolute square root of a squared minus x squared type, okay, I introduced I substitute x for a sine theta. So a sine theta will replace x. In that case, the square root of a squared minus x squared will be the same as a cosine theta if I restrict my theta to this interval. Okay, let me continue next time from this. Okay, anyway, thank you for listening and see you next time.